the string sound. It lets us become, scientists of sound. So what are we actually testing? We've got three main suspects. First up is the string's length. That's how much of it is actually vibrating. Second is its tension, how tight we're pulling it. And third is its linear mass density, which is really just a fancy way of saying how thick or heavy the string is. We're going to tackle these one by one. All right, let's go hunt for our very first clue. We're going to pin down just one of those variables and see what happens when we only change the length of the string. So this first experiment is really simple. We're going to keep the tension and the type of string the exact same. The only thing we're going to mess with is the vibrating length. The big question is, how does that change the frequency, the pitch that we actually hear? So here's how it works. We hang a weight on the end to create a constant tension. Then we take a vibrating tuning fork and touch it to the instrument. We slide this little bridge back and forth along the string until the string just goes wild. It starts vibrating like crazy. So much so that a tiny piece of paper we put on it literally gets thrown right off. That's what we call the resonant length, and that's what we're going to measure. And boom. This shows us our first law perfectly. The shorter the vibrating length, the higher the frequency, which means a higher pitch. The longer the length, the lower the pitch. This is exactly what a guitarist does. Every single time they press a fret, they're just shortening the string to get a higher note. Clue number one, solved. Okay, one suspect down, two more to go. Now we're going to lock down the string's length and put all our focus on the second variable, tension. Right, so for this test, we set the bridges at a fixed length and we don't move them. We'll use the same tuning fork every time, so our target frequency is constant. The only thing we're going to change this time is the amount of weight pulling on the string, which directly changes its tension. And the results are in. The higher the tension, the higher the pitch. The lower the tension, the lower the pitch. This right here is the physics behind tuning any stringed instrument. When a musician turns that little peg, they're just increasing the tension on the string to raise its pitch until it sounds just right. Clue number two, found. We are on a roll. Time to investigate our final suspect, the mass of the string itself. Does a thick, heavy string sound different from a thin, light one? Well, let's find out. So for our final experiment, we keep the length and the tension exactly the same. But this time, we're going to swap out the entire wire for a few different ones, each with a different thickness. Then we'll find the natural frequency for each of those different wires. And here it is, our final clue. A lighter, thinner wire gives us a higher pitch. A heavier, thicker wire gives us a lower pitch. This is exactly why the low E string on a guitar or a bass is so much chunkier than the high E string. You need that extra mass to get those deep, booming bass notes. Case closed. So, we've gathered all the evidence. We know that length, tension, and mass all have a say in a string's pitch. But how do they all work together? It's time to put all these clues together and reveal the master code. We've seen how each piece of the puzzle works by itself. But the really beautiful thing about physics is how it ties everything together. There isn't one rule for length and a different one for tension. Nope, there's one single elegant formula that describes the whole shebang. You ready to see it? And there it is, the master code. This tells us that the frequency, that's the pitch, is determined by our three suspects. Length, L, on the bottom, tension, T, on the top, inside a square root, and mass, mu, also on the bottom. Now, I know it might look a little intimidating at first glance, but guess what? We've actually already figured out exactly what it means. See, this equation tells us everything we just discovered. If you make L, the length, smaller, the frequency F gets bigger. That's you pressing a fret. If you make T, the tension, bigger, the frequency F gets bigger. That's you turning a tuning peg. And if you make mu, the mass, bigger, the frequency F gets smaller. That's you choosing a thicker string for your guitar. It all fits. Okay, so let's do a quick pop quiz to make sure we've got this. According to our formula, what happens to the frequency if you make the tension 4 times stronger? Well, because tension is inside that square root, you have to take the square root of 4, which is 2. So you quadruple the tension, you double the frequency. Simple as that. And what about that thicker wire? Our formula shows that mass, that mu symbol, is in the denominator, on the bottom of the fraction. So as mu gets bigger, the overall frequency F has to get smaller. It's why bass strings are so thick. It all checks out perfectly. So really, the big takeaway here is this. Music isn't separate from science. Every amazing melody, every powerful guitar chord, it's a real-time demonstration of this one beautiful law of physics. The art and the science, they're really just two sides of the same incredible coin. So we've cracked the code. We've found the formula for how a note is made. But think about this. Does knowing the chemical formula for the color blue help you appreciate a Van Gogh painting? Can physics explain why one combination of notes makes you feel